So previously we talked about languages, we talked about strings, we talked about what an alphabet is. We talked about all these concepts building up to languages. We talked about what a decision problem is. But we haven't said anything functional, as in the sense of trying to solve or decide if we're in a certain language or not in a certain language. We have ourselves this concept of a language, and I would like to know if a string is in a language or it isn't in a language. Now, for those that are in tune or learned a little bit about computation before, you may be familiar with the idea that I want to come up with a procedure for which I could decide an answer to that question. And this brings me to something that's quite natural if you think about computers, is think of a machine. Just to kind of put it all together, just as a basic example, you may be familiar with an idea of a finite state machine. If not, that's okay. Oh, awesome, awesome, awesome. Everybody's on welcome here. We have ourselves a blast over here. So you can imagine I have a switch. It turns on or off. It has two states. It has an off state and an on state. And imagine I have a machine that can turn on the switch or turn off the switch. It has two possible states, and to do that requires me to transition from one state to another state by flicking a switch. A very basic, simple machine, right? So every time I toggle the switch, you can imagine this as describing this as whenever I'm in the off state, if I toggle the switch, I go to the on state. If I toggle the switch again, it goes into the off state. And so on. So you might say, Dan, that's an awfully cute little schematic of the flow of how a switch would work, right? It turns on or off, I could toggle, and imagine this is just a button. It could just simply be a button press. So very often people could design schematics for machines based on little flow diagrams like this. This is actually what we would call a transition diagram. It's based on a graph theoretic concept called a directed graph with self-loops. So I have labels on these different states, and I could transition from one state to another. Now, sure, this is cute, right? Like, it describes a very simple machine, a switch. However, suppose I wanted to know something more than just, oh yeah, it's a switch, it turns on or off. But I wanted to answer an ultimate question about this design here. Suppose I wanted to know what sequence of toggles will ensure that when I'm done toggling the switches, that it's always going to be in the on state. So imagine that whenever you get me the switch, it's always in the off state when it starts off. So suppose I toggle the switch. So if I toggle it, so just as an example, if I just do one toggle, it's in the on state, right? However, if I toggle, and then I toggle again, it goes into the off state, right? It goes toggle, toggle. I just follow the arrow with my finger. So I toggle it, it turns it on, toggle it turns off, right? But if I toggle, say 3 times, so I go toggle, toggle, and then I toggle again, suppose this is a sequence of actions that I do. I end up back at the on state, right? Well, if you think about it, I could describe a sequence of toggles, these toggles, as a language. And suppose that each of these toggles is actually a word in my, it's part of the alphabet. So each time I say a toggle, it is like I turn it on or off, right? But what if I wanted to describe a language? So suppose I wanted to describe a language that describes all actions that leave the switch on. So do you see that if I were to try to answer that question, that every time I press the toggle, and I do it an odd number of times. So notice if I press it once, it gets me on. If I go sec 2 times, 3 times, it goes back on. 4 times, 5 times, it goes back on. Do you notice that if whatever that language would be, is whenever I give you a sequence of toggles, that's always an odd number. Do you see that? So do you see how even when I describe a very simple machine like this, if I give you a sequence of actions, which we can think of as input, I can read that input as a sequence. Toggle, toggle, toggle. When I finish reading this, I should be able to know if it's in the on state or the off state. And I could even describe a language, perhaps we're going to talk more about this, of the ones that leave the switch on, just as an example. So this is me motivating the idea of a finite automaton, or finite automata if we're talking plural. Either way, these are all manifestations of the same idea. But that brings me to talking about what I just described to you. Okay, we're going to be describing a machine that its job is to decide if a string is in a language or isn't in a language. As in, we're going to decide if the input belongs to a language or not, and we want to design the machine such that it will recognize a given language. Now, that's going to be the framework we're going to work within. Is that clear, everybody? So let me describe this for you. So how a finite state automaton processes strings is by reading the input string. This is the convention we're going to pick up, is reading the input string left to right. Left to right. So you're going to imagine you have some input that's provided to this machine. Let me draw a fun picture to kind of put what we're putting in place here. So you imagine I have my machine, my finite automaton. Here's my machine. And this is the framework that we're going to work within. And I must stress that by adding features to this machine, we can potentially decide more languages by recognizing them, right? But what we're going to talk about are just finite state automatons. So they means that they're going to have a finite number of states, just like I have 2 toggles here, like two possible states I can toggle between. They're also going to have a couple limitations as well. So let's talk about that now. So this is kind of the big picture. So you can imagine that the input is provided as a string. And you can imagine it's like a piece of tape that's fed into the machine. If you've ever seen something called ticker tape before, it's kind of like if you imagine the tape's getting loaded into the machine and it starts right on the first symbol of the string, starting on the leftmost side. So you can imagine it reads in tape like this. Now, I must stress that this is just a picture. It doesn't have to look like this. So imagine I give you a string W as input, and it's going to be read from left to right. So it's going to be pulled through here. And you imagine it's on this tape. And the finite automaton has a reader. It has a reader. And it starts on the first symbol in the string. And what it will do at a high level is it's going to read each one of the symbols on the string. And it will react based on what the input is. So this will mean it will transition from possibly one state to another state. And what would be desirable is whenever I give you a string W, that when I finish reading the string, that it's sitting in a state for which it will tell me if it belongs to the desired language or not. So just like I was talking about, oh, which strings would give me, or you think of these as strings, which ones would leave me in an on state versus an off state. The same thing here. Just it's a little bit broader. So you can imagine this is a figure showing you what one of these finite automata might look like and its capabilities. But it doesn't have to literally be this. It's going to have actually a formal definition. So this is just a high-level view of how this will work. So let me just summarize this. So given a string w, which is going to be x1, x2, all the way up to xn, the DFA, so if you're wondering what a DFA is, I'm going to define this in a moment, but it's a deterministic finite automaton. You'll see what I mean by deterministic in a bit. The DFA begins in an initial state what we'll call conventionally Q0. It doesn't have to be called Q0, it's just the name we're going to give it for our definition. Then, based on what we're going to call a transition function, which we're going to define in a little bit, a transition function, which this will define how we go from one state to another state, just like on our example here, where I say, oh, to go from the off state to the on state, you have to toggle. Just in the same vein that when I want to go from the on state to the off state, you have to toggle. So this would be defined by this so-called transition function. This transition function, and we'll call it delta, lowercase delta. Sorry, no, not delta. Yeah, lowercase delta. Delta. I get my symbols sometimes a little mixed up. I'm just having a little bit of fun about this. Symbol x1 is read and based on what x1 transitions to, it transitions to another state. And so on. So what will happen is x2 will be read next, and then it may potentially transition to another state, and so on, and so on, and so on. And then finally, xn is read. So let me just maybe put a number on this, 1. Then there's stuff that happens in between. Then there's finally xn is read and may transition to another state, right? And if the DFA, I'm just going to make some more room here, and if the DFA is in a state that belongs to the final or accepting states, it accepts. Otherwise, it rejects. So I don't have enough room there to say, but it's otherwise rejects. I'm going to define this all in a moment. So I'm just trying to give you a high-level picture of what we're going to be in for when we talk about a deterministic finite automaton, or plural deterministic finite automata. So there's this notion of acceptance and rejection. So it either accepts or rejects W. So it's got to do one or the other. It can't do something in between. It has to do one or the other. So let me now define what a deterministic finite automaton is. And remember, it doesn't have to look like that picture right there. It doesn't at all. It's a mathematical. There's that dreaded M word again. It's like mayonnaise or mustard. It makes good sandwiches. It's a mathematical object. But the point is it's still a machine. It's an abstract machine. It's an example of what we call an automaton. It's an abstract machine. It's a type of model of computation. Given it's all of its faults and great things it can do. Deterministic finite automaton. Which, this is a DFA. So whenever I refer to a deterministic finite automaton, I'll refer to it as a DFA because it's a bit of a mouthful to say that every single time. So one thing I need to point out is that DFAs, they aren't just simply just some model of computation. They also can be used for all sorts of different things. So many practical applications use these types of objects or equivalent formulations of these things for things like string parsing, for doing types of what we call lex analysis, and also all sorts of other problems as well. I mentioned, for example, you could, for example, test a circuit using formulations like these. But there's many equivalent ways to define the languages that can be recognized by one of these DFAs. So let me define a DFA with you, and then we're going to do some examples so you can see what it's like. We could play around with it. We're going to design some DFAs, and then we'll see a bit more from there. So hopefully you're getting a little excited. I know I am. I know I'm very excited about this. But I will warn you, at first this is going to look really intimidating if you've never played around with mathematical objects that have more than just two pairs, or a pair, like a graph or something like that. This is going to look a little intimidating, but I assure you, there's nothing scary about it. It's very intuitive. Just think of our picture over here. So it's going to be a quintuple, or a five-tuple. It's going to be, I'm going to call it A, but remember this is just a name for this DFA. It can be called whatever you want. It's going to have 5 parts to it. Q, capital Q, sigma that you might recognize as an alphabet. Delta is the transition function. Q0, we said that was the initial state, and we're going to have what we're going to call our final or accepting states F. So this is our set of states. This is the set of accepting or final states. So let me just lay out what all these are. So Q is a finite set of states. You might ask, Dan, why is it called a finite automaton? Notice that there's a finite possible number of states here. It's the first dead giveaway. Next, sigma is a finite non-empty set of input symbols. So notice that we're talking now about input symbols, and it will remind you just of the definition of an alphabet, right? Next, we have delta is a transition function. This is going to be the tricky one for me to define for you. But once you get it, it's not too bad. Is a transition function. It's a transition function. Let me just switch markers here. I'll give you a moment there. So delta is a transition function. So delta is the name of the function, just to be very clear. That takes as inputs / arguments, whatever you would like to call them, as inputs or arguments, a state. So it takes a state and a symbol. and a symbol. Then returns a state. So you give me, what, Miss Kitty? What? Yeah, I know, we're talking about DFAs. What do you think, Miss Kitty? Yeah, no, Miss Kitty, the transition function, it's going to take in as input a state. Yeah, exactly. Yeah, a state and a symbol. And then it's going to return back a state, Miss Kitty. Yeah, exactly. So more formally, how you would define this is as follows. So the fancy way of writing this down, more formally, delta is a function that takes a state and an input symbol, and it outputs another state. That's all this says. Right, Miss Katie? So that's what a transition function is. We're going to see examples, so don't worry if this looks a little daunting. Don't worry, it's all good. So remember, this is what's, just like in our toggle example we had over here, its job is going to just simply say, I give you a symbol that's going to be read. I'm going to transition to another state. So I have to be in a state at that time, right? Every time I'm executing, I'm in some state. That's the point. You're in a current state, you read a symbol, then you tell me where to go. That's all this says. If you want to think about it as a lookup table, that's a very intuitive and very perceptible way of looking at this. Next, Q0 is one of the states. So it's among the states Q is the start state. So there is one state that is dictated as the start state. So this is the state the machine begins in. So if it doesn't read anything, it just is in the start state. So once this starts up, it's going to go from the start state to potentially other states. Then finally, F, which is going to be a subset of the states, is the set of final or accepting states. So either one is fine to say. It's pretty common to use either one or the other. So the point I'm getting at is that when the DFA reads the input, it transitions from state to state to state, but each time it will gobble up one of those symbols and when it's reading it. So this tape is you're gonna imagine like tape going through this machine, and when it's finished reading the input, it's gonna tell you an answer. It's either gonna say accept or reject. We say it accepts if the state that I'm presently in at the end of reading out that input is in F, then we accept, otherwise we reject. So I'll have a more formal way of talking about this in a bit. But for now, I think it's a good idea we see an example. So I thought it'd be a good idea you see an example where I just use the definition directly. So that way we're not talking at a higher level or anything like that. We're just sticking directly on our definition, and then we're going to see ways we could describe DFAs in other matters. You're going to see that there's at least a couple helpful ways to do this as well, other than the formal definition. So let's do an example. Suppose DFA M1 equals the following. So as S0, S1, S2. So remember, the first of the 5 tuples is the set of states. So these are our states. The states are S1, S2, and S3. Sorry, S0, S1, S2. Sorry, getting really excited here. Then we have our input symbols. Then we have the transition function, which I'm going to describe below this because it takes a little while to frame it. Then we have S0. S0 is going to be the start state. So the DFA is going to begin in S0. And the final or accepting states is going to be S0 and S2. So these are our final states. Where, now I'm going to define for you the transition function. Where, now remember, the way this works is that I give you a state and I give you an input symbol and you have to tell me where you're going. So if I'm in S0 and I read a 0, then the DFA is supposed to go get into a state S1. If I'm in S0 and I read a 1, I go to S0. If I'm in S1, state S1, and I read a 0, go into S0. If I read an S1 and I read a 1, I go to S2. Next, if I'm in state S2, I read a 0, I go to state S1. And finally, if I'm in state S2 and I read a 1, M1 goes into state S1. So this is a complete description of the transition function. Note that you have to define every one of these. Otherwise, you have not defined the transition function. The transition function here is required to have it where you give me a state, you give me an input symbol. So you have to define for all possible states and all possible input symbols where you're supposed to go. So notice, and the reason why it's deterministic is notice that whenever I'm in a state and I read a symbol, it goes to exactly one state. They can't go to a set of states, for example. That's a whole other concept that we're going to talk about maybe sometime in the future. So remember, that's the set of states. This is the input symbols. This is a transition function. Please note that for every state there is an input symbol. And that means that all of these are defined. You can't omit these unless there's some construction you have that tells you what you're supposed to do in all other cases, okay? And finally, these are our final states. So S0 and S2 are the final states. Now, let's talk about processing different strings using this definition. So please, let's follow carefully this process. So I'm going to do this at a higher level. So I'm hoping that you understand how this is going to work. Okay, remember, you're going to start off, you can imagine the reader is on the first symbol. And every time it reads a symbol, it's going to imagine it's going to pull that tape just one over to the next one, and it reads that one. Each time it'll perform a transition as per the transition function. And when we finish reading the input, it'll either accept, so M1 will either accept or reject the input string. So let's do an example. So suppose W, the input string, so suppose that the input W is the following binary string. It is 1, 0, 1, 0, 1. So it means that when we start up, we're going to be in state Q0, and we're going to begin by reading this 1. So first, it begins in S0. So what's the first thing it does? It reads a 1, right? It reads the first symbol. It reads 1. But if it's in state S0 and it reads a 1, where's it going? Where's it going? What is the transition table? Well, sorry, our transition function. I'm getting ahead of myself. This looks awfully a lot like a table. That is not a coincidence. It's a very meaningful way of thinking about it, like I said. But remember, I'm in S0. I read a 1. It says to go to S0. So we're staying in S0, but we're transitioning there, right? Then we transition to state delta S0, 1, which is S0. Now, we finished with 1. Now let's read the next symbol. Next symbol, we read 0, and we transition to state. Which state? We're in S0, right? We read a 0. So we're in S0, we read a 0, it says to go to S1. So we're in state S1 now. Read the next symbol. We're going to read a 1 next. So we're going to transition to the state dictated by the transition function. So right now we're in S1. We read a 1, right? So we're going to appeal to this one, which says that S1, when I read a 1, is equal to S2, right? So now we're in state S2. Well, M1 is specifically. Next, we read the 0. You read 0. You transition to which state? You transition to state dictated by the transition function, S2. You read a 0, so S2, 0, says to go to S1. So now we're going to be in state S1. And finally, we read the 1, the last symbol on the input string. You read 1. We're going to transition to state delta. And right now we're in state S1. We read a 1. So that means that we're going, so we're S1, you read the 0, no, read a 1, right? Because the last symbol is a 1. We go here. Notice it says it's S2. Now, will the DFA accept or reject? Remember, what's the state that the machine M1 is in upon reading W over there when we're done? It's in S2. So right now, presently, M1 is in state S2. But S2 is one of the final states. So does it accept or reject? Accept, reject. You only can do one or the other. Accept or reject. Does it accept or does it reject? So is M1 accepting or rejecting here? Well, most certainly it's in one of the accepting states. Accepts. Very good. So finally, I'll throw step 7 up here. Step 7, it accepts because M1 is at or in state S2, which is a final state. So I'll give you another example, now I'm not going to work this one out for you. It's going to be in the notes. But here's another string, 0, 0, 1, 0. If you look at this carefully, if you walk through the same process, so imagine I give you that the input string is 0, 0, 1, 0. I will tell you that this case it will actually reject. So I want you to take a look and try and go through the same steps using the transition function, and this one will actually reject. So in fact, there's more strings. I've also included some more in here. Some I've worked out, some not so much. 1, 1, 1, 1. I think how many ones do I got here? I was being very dramatic when I was doing this, okay? That's how I live sometimes. So that's not literally, I mean more in an epic way, okay? The cool kind. So I got 7 ones. In this case, it accepts. So I encourage you to try walking through with this example. Also have 3 zeros. It rejects in this case. So I encourage you to try walking through this process with each one of these. In fact, I have some other ones too, but I'll leave those in the notes, okay? So this can be somewhat lengthy to do, to describe the 5-tuple description. So this is actually like the formal description of the DFA. So if ever somebody asks you for the formal description of a DFA, they're asking for this. So this can be lengthy to do. So there's actually a couple other ways to describe a DFA. So let's talk about this. I would argue that these other ways are simpler. It's important that when you do it, you're following some kind of conventions that are easy to parse, okay? So just to be clear, this is a formal description of a DFA. So this is a formal description. So if anybody asks you for a formal description, you could do this. But this could take quite a long time if you have many, many, many states and many, many transitions. There may be a more concise, so whenever you see like the infomercials and they say, there has to be a better way, I'm going to try to give you a couple of ways to do this that are a little simpler. So here's a couple other ways to describe a DFA. So the first one, I alluded to this already, is the idea of a transition table. A transition table. So just think of a lookup table. If you've never heard of one of these before, I'll explain. Because that's what it is. It's a lookup table. This is how very often you might even implement such a thing. You might implement it as a lookup table. It's not the only way, but most certainly that's one effective way. I know somebody, especially if you have more of an engineering background, that's probably the first thing you might think of trying to do. So what do you do here? You list all the states as rows and all the input symbols as columns. If given a state and a symbol, the state to transition to where would it be? If you imagine this as states are rows, the input symbols are columns, all you do is just do this, right? You just do this. They're going to meet at the intersection of the row and the column. Transition 2 meets at the current states row and next symbol red's column. Just as an example, just so you can see, because I'm going to use the same thing I have over here. So just to make this a little easier for us to do, I'm going to actually write out the table over here, just because I have the formal description here. It'll be a little easier for you to evaluate for yourself if that in fact is the thing we actually just did. So I'm just going to move over just a little bit, that way you can actually see what we're doing. I just want to make sure that you're not feeling like, oh, Dan's just saying stuff again. is that I can double check this, although that's how I usually do things, but you get my point, is that I want to make sure that it's clear where this description fits in the table, okay? So as I said, we're going to make a table. So I'm going to make a transition table for M1. So each column is going to be one of the input symbols, and each row of this table is going to be a state. So I'm going to have a state for each one. Each row has a state. Each column has an input symbol. I told you it's just going to look like this. It's nice and simple. Now, there's a couple of things I want you to be aware of. First, whenever we label the start state, you have to have a clear symbol for the start state. It's quite common to use an arrow to indicate the start state. This is just a convention. And also another common convention is that use stars on the labeling of these rows just to indicate that those are the final states. So you'd agree with me, the reason why I put stars here, because these represent the final states, because S0 and S2 are the final states. I put an arrow on S0, it's because that's the start state. Now, all I do is I look at what I have here. Do you see how this looks just like, I could just read this off, right? So S0, when I read a 0, that should be right here, right? So I have S1 right here, then S0, then S0, S2, and then maybe down here I have S1. What would go right here? What goes in that spot right there? Just to be dramatic here, let me get my pointy sticks out. There we go. I got my pointy sticks. Okay. So I'm given I'm at state S2. I'm given a 0. S2, given a 0. What should go in this spot right here? What goes right there? Which is what you see over there, right? I had to do that for flair, okay? So the reason why it's S1 is because notice that each row is telling me this is the current state. You can imagine this is the state I am in. When I read a 0, where I meet at the row and the column where these two meet, that should be the output of the transition function right there. See, notice that the output of this would be S1. Likewise, right beside it is S1 too, because when I'm in S2, when I read a 1, that's right here. When they meet together, it's S1 there as well. Hopefully that is clear. But yeah, so this is an example of a transition table for M1. Isn't this a little easier to understand than that? At least it's a little easier to write down, right? It's not, you don't have to write all these deltas and all that stuff. It's a little more concise. So this is a transition table for M1. And notice that I'm not losing anything by describing it like this. There isn't anything lost in the description. Quite intuitive, right? Is there any questions about the transition table? Is there anything, all that Dan is saying weird stuff again? I think I transcribed them all correctly. Okay, if I don't have any questions, so why don't we proceed? Let's talk about the other way, a very common way of representing these. And it will remind you a lot of the example I did with the toggle machine. So I had the machine that just toggled. The second one is a transition or state diagram. So this will remind you a lot of what we just did when we first started talking about DFAs. Okay, so it's going to take a little bit of time for me to describe it to you, but it's going to be very intuitive, okay? So I just need to make sure I lay it out so that we understand all the rules for how we draw these out, okay? Because it's important that we understand what we're doing. So a natural way, a natural is subjective, most certainly, But I'll say that if you could characterize something that you're looking at as a graph, it can often look quite natural for problem solving. So we can ask all sorts of questions about DFAs on a graph, for example. That's what I mean. So for somebody that's a problem solver kind of mindset like me, that thinks about algorithms, it's very natural to think about it like this. So over there, like that is very natural for thinking about it if you just wanted to implement one of these things in hardware or something of those lines. This is much more natural for like a higher level kind of problem solving way of thinking about it as well. Now, both of them are ways, completely valid ways of representing these things on a computer as well. So just be aware of that. Sorry, I'm just getting really excited. Naturally describe. A natural way, oh, instead of saying describe, let's use the word represent. Just to change it up, you know, just add a little garlic instead of salt and pepper. Represent automata. Remember, that's plural. Automata is using labeled directed graphs. Directed graphs with loops. Now, if you have no familiarity with this concept, I do actually have a series on graphs, so you can check out that series if you want to learn more about this terminology. You're going to see it's not that complicated for what we need. I like to think of graphs as fairly intuitive. At least when you talk about them, it's the terminology that sometimes gets people. That is, we can construct a transition diagram as follows. So we're going to have vertices for the states. That's the first thing you need to know. There are vertices for the states. So for each state Q in the set of states, there is a vertex labeled Q. That's the first thing. So naturally, I'm going to need more space, so let's go over here, okay? So just keep in mind, kind of like our toggle example, which we had two states, we had a vertex, but now you can think of it as a vertex if you want. Now you can think of that as each one of the states, they have a label that represents that state. Just like if I talked about my toggle example, you can imagine I have an off state and an on state. That's literally what they're called, off and on. The next, we're going to have directed edges, which are called arcs as short, or sometimes we'll just refer to them as edges. These are going to represent the transitions. Or transitions from a state to another state. So for input symbol X, which is in the input symbols, and state, or potentially states, PQ in Q, because keep in mind you could stay in the same state. If delta Px is equal to Q, then the diagram includes arc PQ. There's going to be a directed edge from P to Q. So that's an arc from P to Q, and it's going to be labeled with something. It's going to be labeled X. That's the input symbol that got me there. Now, we're going to try to keep this graph so that it is simple in the sense that we're going to allow loops. So it's going to be a simple digraph or directed graph, but we also allow self loops. So it's not technically simple, but it's not going to have what we call parallel or multi-edges in this graph. So the way we're going to handle that is because you can have it where you go from one state to another, but with multiple symbols, is for simplicity, if there are multiple input symbols, X in the input symbols, where it goes from P to Q with delta Px is equal to Q. This means I'm in state X, state P. Sorry, I'm getting really excited here. I'm just flowing with this stuff. Go from state P, given X, I go to Q. Then one can label arc PQ with a list of all such input symbols. So you just have a list of symbols as opposed to just one. So you can almost think of it like each label will be a list of all such input symbols. If you don't like that, you're all welcome to turn it into a multi-graph too, with multi-edges. But you'll find that it doesn't need to go that far. 3. Once you've done this, you indicate the start state. You include an arrow. Toward the vertex. That is Q0, the start state, from no other vertex. So it's just going to be some weird disjointed arrow that just points at this one, okay? You're going to see in the moment. From no other vertex. And finally, you're going to label the final states. So we're going to walk through these steps to build. So we've got to indicate the final states. So don't forget to indicate the start state and indicate the final states. Just please don't forget about those. What you do, the common convention here is you double circle. you double circle all final states. Here, let's see. Q0. Yeah, Q0. It does sound like that. But let's walk through this step by step, and we're going to build the transition diagram now. So let's build this sucker. So fortunately, I have the transition tables just sitting right here, so we can actually use that. And it's going to have 3 states. So I'm just going to get a different marker here, because this one's starting to act a little funny on me. So we're going to have 3 states. We have 3 states. 1, 2, 3. So I have 3 states, right? I have S0. So you might ask, Dan, how do you know to put them like this? It's mostly experience. Keep in mind, there isn't just one drawing of the transition diagram. It's meant to convey information or data about the DFA. It doesn't have to look like this. But the things that do matter when you actually are talking about what it looks like are what the connections between the vertices or states are, and what the start state is and what the final states are. That's what matters. Not the positioning of where the nodes or vertices are. That doesn't matter. So let's look at our transition table over there. So it says S0 on 0 goes to S1. So let me draw an arc. I'm going to label that with a 0. Right, that's what it says to do over there. S0, when it's in 1, when it reads a 1, it stays in S0. So I draw a self loop and I label it with the input symbol that would get me back there as per here. So this is actually just the first row here. I know that S0 is the start state, but I'm not going to do that quite yet. I'm not at step 3 yet, but I could technically just label start state now, but I'm just trying to keep this simple for us. Next row. When I read a 0, I go back to S0 from S1. So I'm going to draw transition like this. Right? That's what it says. When I go from S1, I read a 0. Remember, I just follow it with my finger. That's how you know the transition is occurring, just like when we talked about earlier. Next, it goes to S2 on reading a 1. When it reads a 1, it goes to S2. And that's the second row, the last row. S2, it goes to S1, regardless if it's read a 0 or a 1. So I just say 0, comma 1. So I just indicate all the input symbols that it transitions from S2 to S1. And that's all of that's the transition function. I've encoded that information into the diagram. So I have so far followed the first 2 steps. Next, indicate the start state. So very commonly, I'll just write start on it just to make it a little clearer that, oh yeah, this is the arrow I'm referring to. It doesn't come from any other vertex. I usually put start on it just to make it a little easier to see. I think it's cute, but at the same time, it makes it clear that that is the case. But as I mentioned here, it's just an arrow suffices. Then finally, I got to double circle the final states. Well, S0, remember in our transition table, I said S0 and S2 are the final states or accepting states. So I'm going to double circle them. So I'm going to put another circle inside of my circles. And there we go. That's our transition diagram of M1. You may have heard of this term before, but here's one way of defining it. Is defining something called a regular language. So you might ask, Dan, what the heck is a regular language? Well, let me define it for you. So this is one equivalent definition for a regular language. I say already too many things, but a language L is regular. So this is just a name for these types of languages. It's regular if some DFA recognizes it. So that means that you could design or discover a DFA that for every input of that language, it should be able to accept. So it recognizes that input, and everyone that is not in that language, it rejects. So there's many different ways of formalizing this concept of a regular language. Most certainly, as we explore more theory of computation, we'll see that it is actually a rather fascinating equivalency that exists for this definition. But this is one possible way I could define them for you.